and welcome to my video lesson 7.4 on half-life. We're talking about the half-life of radioactive atoms and what those half-lives look like, what the formulas are, etc., etc. So just to start, half-life is the time it takes for half of an atom type to decay into another type of atom. So for example, carbon-14 is probably the most famous isotope. So famous that I even forgot the dash. Oh, that's interesting. So famous I even forgot the dash here. So carbon-14 is decaying into carbon-12. But this takes a long time, right? So if you have 1 million atoms of carbon, 500,000 will have turned into carbon-12 after 5,730 years. Or another way to say that, or better way to say that, is 500,000 of them will have turned into this. 50% of them will have turned into this after that much time. And different atoms will have different half-lives. So you can see I tried to find a range of half-lives for you to compare to. But this is a fairly stable atom. If you look at your formula sheet, uranium likes to be at 238. So it's quite stable where it is, right? But these other ones, they're a lot less stable. Potassium is okay, but it normally wants to be at 39 mass, so it's not super happy there. But as you go this direction, you can see that we have some half-lives of only a couple days. One that's kind of interesting is strontium-90. Has a half-life of 29 years. So a lot of humans that are alive right now, I assume I have it as well, have strontium-90 in their bones because of the nuclear explosions for nuclear testing and whatever that happened in the 60s, 70s as well, 50s and 60s mostly. That released radioactive isotopes into the atmosphere, and some of those decayed pretty quickly, and some of them decayed into strontium-90, and strontium-90 has a longer half-life, and usually we consider after 10 half-lives, then most of the substance has changed, and so it doesn't matter anymore. But 10 times 29 is 290 years. So it'll be another, well, because it was the 50s and 60s, it's been about 70 years. So that means maybe 2.5 half-lives have transpired already since then, but not nearly enough to get most of it gone. Well, most of it's gone, more than half of it's gone, but not all of it. Okay, normally 10 is what we start calling it, where it's basically gone. And depending on what you're looking for in archaeological sites or whatever, you can use different types of dating. Geology is going to use some of these much longer half-lives, whereas if we're talking about human buildings and stuff like that, we're probably using, or mummies, we'll probably use carbon-14's half-life. So usually about 10 half-lives. Anything beyond that is kind of unmeasurable because 99.9% of the material is gone. Original material is gone. The equation is given like this in your formula sheet, but it's not super clear because N is actually the number of half-life periods. And that's more difficult to actually be able to tell. So you need to understand this, and this is not in your formula sheet. Okay, where N is the time, and you can have whatever units you want, days, years, whatever, and P is the half-life of whatever material you're talking about. Now, this is a really cool equation if you're talking about the math behind it. It's an exponential equation where N is your unknown, or your X, or your variable, or whatever, the lowercase n up there. So it's kind of like, I don't know. It's kind of like this formula here. So if you want to graph it in your calculator and see what the graph looks like, this is a very common-ish equation to graph in Math 30-1. And so we learn about logs, and you can solve this with logs. Now in Physics 30, we don't really deal with logs very much, but let me just say that if you have a situation like this, you can solve for x using a log. That's the whole point of a log. So a log of base 10 of y equals x. And so this is how we can switch from one form to the other, from an exponential function to a logarithmic function. And by doing that, you can solve for whatever you want. So in our example here, I'm using 100 as like 100%, that's the idea. And then it's 1/2. And then to the exponent x. And if we graph that, it won't actually show up very well because we're talking about some pretty big numbers. So what we want to do is make our y maximum 100 and our minimums 0. And then we can see it a lot better. And this is what a decay curve looks like. So after, and each of these ticks down here is one half-life period. So after one half-life, half of the material is gone. Right? After two half-lives, 3/4 of the material is gone. Right? And then you cut that in half again, in half, and half, and half. Right? So that's what the decay curve looks like. And this log idea can be helpful, but isn't necessary in Physics 30. Okay, so given these couple different equations, we've got a lot of examples here. Given the half-life of polonium 100 is 138 days, if the sample starts with 36 grams, how much is left after 2 years? Try these examples yourself, and pause the video, and then press play once you're ready. Okay, so this is the formula, right? But I'm going to use T over P, right? So what we're going to do, we're wondering how much is left. So that's this N over here. That's what we're looking for. So we don't actually have to rearrange anything, which is kind of nice. So we're going to start with 36 grams. We're going to have 1/2 here. And then it's going to be to the exponent of T over P. Now, it's 2 years. So 2 years times 365 days per year. So it's 730 days. 730 days. 138 days is the half-life period. And so now we can plug this in our calculator and get our answer. And we get 0.92, let's just leave it there, 0.92 grams because we've got 2 sig digs. Okay, so not a lot is left. Basically 1 gram is left after 2 years. Okay, again, pause the video, try the next example yourself, and see if you get the same answer I do. Okay, if the half-life of carbon-14 is that long, all living organisms have the same ratio of carbon-14 versus carbon-12 because we replenish it from living organisms like plants and animals. And so we replenish and we have the same ratio every time. So anyways, it's 1 part per trillion carbon atoms is carbon-14. That's what it is to begin with. If a body is discovered frozen in a glacier, and we try to figure out how long it's been there by comparing the living value with the value of the body, if the body had been there for that long, then what would be the new ratio of carbon-14 to carbon-12? So let's just, instead of putting in like a number, let's just say we have, well, let's put in the ratio. So 1 part per trillion. That's 1 million That's a billion. That's a trillion. So 1 part per trillion. Or actually, no. Let's do it differently. 1 part. So let's say it's just 1. Let's just call it 1. Let's see how much percentage of that 1 is left. This will be more straightforward. 1/2 after 9700 over 5,730. So what we're doing here is we're figuring out the ratio or the percentage of how much is left. So we get 0.309. So that means 31% roughly is left after that much time. So what we need to do is, it used to be 1 to a trillion. This is a million, billion, and a trillion. But now what it is 0.309 to a trillion. So if we want to, we can change this. Sig digs are not clear. We probably have 1 sig dig. So let's just call it 3, and we'll just move this over by 1. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So now it's 3 in 10 trillion. So 3 in 10 trillion is the new ratio. So all we had to do to move that decimal over, we moved it over 1 here, and we also moved the decimal over 1 position here. Right? That's all we did. Okay, an inverse example. Let's see if we can solve this one. A sample of 256 million atoms of strontium-90, which has a half-life of 29 years, is inside the bone tissue of humans due to the nuclear testing, so like I talked about in the 50s and 60s. How long until there's less than 1 million atoms of strontium left? So 256 equals, and we want to get, oh sorry, I said that wrong. We want to have 1 million left. Right now there's 256 million, and then a half-life. But the problem is that this is T over the period, which is 29 years. But the problem is I can't figure out the T. So how can I solve this? Well, we can solve this by hand. I don't think this would be required by Physics 30, but I think technically maybe it could be. So what you're going to find is that we have this sort of thing happening. And what you can tell is that 256, I guess this could be Physics 30. 256 is a multiple of 2, so we just have to figure out by kind of induction or whatever, 2 to the exponent what is 256. Now, 256 is an exponent of 2, so we're just going to try a couple things. Let's just try 10. That didn't work, so 2 to the exponent 8. There you go. That was pretty straightforward. So 2 to the 8 is 256. So that means that this is true, right? And if this is true, then what we can do is we can take the exponent here and make it equal to the exponent here, because they have to be the same. So 8 equals t over 29. And then we can solve for the time. So 29 times t, or times 8, sorry, which is 232 years. So if you're given a question like this, it must have a easy quote-unquote answer to solve for. If you were just to randomly guess, it would take you forever to basically guess this number, but it is possible to solve it like this. There are ways to solve it elseways as well. You can certainly just do this, 256 times, and then basically what we're doing here is we're going to be finding the intersect between these 2 points, or these 2 graphs, I should say. We're going to need a long window setting of 300 or so. Okay, and so where those 2 intersect is also going to be the same number. You go over where you think it is, enter, 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 and you'll notice we get the exact same answer. So if you, all I did is take this as one of my 2 equations. So this is like, let's say y1, and this was my other equation, y2, and then I found the intersect. Okay, so there's multiple ways to do that. Let's just talk about 2 other ways we can do it, which again are beyond Physics 30, but it's interesting to see and to practice because you will see it in university. A logarithmic example here. So if you think you can do this, pause the video now, try it out, but otherwise take a look at what I'm going to do right now. So we're going to set it up the same sort of way. Right now we have 100 moles of cobalt-60 with a half-life of that, and decays with only that much left. So at the end we have 20, at the beginning we have 10. Now it's a half-life, so that's why we're using a half here. That's always what we're doing. And then it's T over the half-life period, so 5.26. Now, we can solve this algebraically if we use logs. So what we're going to do is divide by 100 on both sides. And we get this, or 0.2. Okay, so this is fantastic. And now what we have to do is use the basic log rule. The basic log rule is simply that we have log of the base, log base of the answer, equals the exponent. This is the basic log rule. So normally it's base to the exponent equals the answer. So a log just kind of inverts this, right? So what we're going to do exactly that, and we're going to invert this. So it's log base 1/2, or 0.5. Okay, and then answer of 2, so 0.2, equals T over 5.25. So then we're going to move that over, so it's actually going to be 5.25 log base 0.5 answer of 0.2 equals T, and we're looking for T. So now what we can do is show this in one other method. So we showed it with the kind of guessing method and making the exponents equal. We showed it with graphing. Now we're going to show it with logs. So 5.26. That should be a 6. 2.26. I made a mistake previously. And then log, which is in the math button, because we want to have log base, which allows us to type in 0.5. And so we get 12.2. And this would be years. So this should be 25.26. That should be 0.26. I'm just correcting my previous mistakes here. But the correct answer here is 12.2. Now, it looks like we only have 2 sig digs because we have 2 moles, so 12 years. Okay, so like I said, it's not too bad. All you have to do is practice using this skill here. So I recommend you pause the video and try example 5 on your own. Okay, so let's see if we can do example 5 now. So 100 grams of it decays into 6.25 grams. So we set it up the same way as before. We're wanting to know the half-life. So in this case, it's kind of telling us a different number. So we're looking for that period, that half-life period, which I'm calling P, but you could use a different letter. And we just have to slowly rearrange and solve. So 6.25 over 100 equals 1/2 to the exponent 10.8 over P. Okay, now we take, we're going to rearrange it into the log base thing. Actually, before we do that, let's find the actual answer here, which is 0.0625. Okay, so this is going to be log of the base, which is 1/2, so 0.5, of the answer, 0.0625, equals the exponent, which is 10.8 over P. Okay, so I use my log rule. Now I need to solve for P, so I'm going to move the P over and divide by the other part. So it's going to be P equals 10.8 over log base 0.5 of the answer, which is 0.0625. And that will be our final answer there. So let's now plug it into our calculator. 10.8 over math to get to the log base. So I press this math button to the log base. The base was 0.5 or 1/2, 0.0625. And so we get 2.7 days. So that is the half-life of gold 198. All right, I hope this video helped you better understand the half-lives, and just a reminder that really these first 3 examples are ones that we would see in Physics 30. The first 2 are easy. The third one is difficult, Physics 30. Example 4 and 5 we wouldn't see in Physics 30, but they're not too bad either. And once you know this, it actually can speed up previous examples as well. I hope this video helps you better understand half-life, and good luck.